So in this talk, I will be talking about how to efficiently and correctly schedule test traces for ensembles of network policies if you want to test stateful networks. So this is a joint work with Sanjay, Limi, and Vyas at CMU. So we know that today network operators have to enforce a large number of network policies in order to ensure the availability, security, and performance of a network. So in order to, for instance, those policies are such like reachability, service chaining, and access control. To ensure that those policies are correctly enforced in the network, a practical approach is to run network testing by injecting a large number of test traces into the network and see what the behavior is of each traffic trace. Indeed, in recent years, we have seen a lot of great proposals aimed at how to efficiently generate those test traces if you want to test a single policy. For instance, we have seen ATPG, PMesh, BUS, and SIMnet that are proposed in recent years. So typically what those tools does is sort of they take high-levelly two parts of inputs. One is a high-level policy, and the other part is going to be a model that models the network. And as output, they efficiently generate the test traces that aim to test those policies. So to understand what is happening in practice today in terms of networking, network testing, we ran a survey in September 2017 among about 30 network operators. And first of all, we found that operators today have to enforce multiple network policies. As you can see in this figure, about 58% of the operators we surveyed say that they have to enforce 10 to 100 network policies, and we also say that there's a reasonably large number of network operators say they have to even enforce even higher number of network policies. So as a result, this is not surprising that they have to use different tools to test different policies. In particular, we found that all the network operators we surveyed said that they have to use more than 5 different tools. In particular, there are 50% or half of them said they have to use 5 to 10 different tools in order to test those policies. Finally, what we found is that in practice, operators are still relying on running live testing. So what does it mean? That they have to inject all the traffic into a network and then see what the behavior is to each traffic in order to determine whether the policies are correct or not. Unfortunately, even though we have seen so many great proposals on how to efficiently generate those test traces aimed at testing policies, we found that actually how to run the test traces in a naive network itself can be very challenging. In particular, there are several naive solutions, and they would not work particularly in a stateful network. For instance, the first naive solution is to run all test traces in a sequential order. Namely, we can inject one trace at a time, and then wait for sufficient downtime, and then run the other. As you can imagine that this scheduling or running is not going to be scalable if you have a large network with thousands of test traces you want to inject into the network. So a second naive solution you might wonder is that can we just run them together into a network and see what happens to the test traces? This is a parallel injection. Well, on one hand, it can significantly reduce the running time, but however, the results by scheduling the test traces in this way might give you incorrect results. To illustrate why this can be incorrect, let's consider a very simple example here. Suppose we have a stateful network shown in this picture. We have a firewall connected with an internal network, and we have an external network. And suppose the operator enforce 2 policies in this case. At the first part, the operator enforces the policy that the firewall should always allow all packets sending from the internal network. And at the second part, the operator enforces another policy, which basically is saying that, excuse me, if you have a packet sending from the external network to the internal network, then this packet should be blocked if the receiver in the internal network did not send a packet to the sender in the external network before. Now imagine the operator uses two different tools to test this policy, to test those two policies. Then a particular case would be there are two test cases. One requires to send some traffic from some internal hosts in the internal network, I1 say, to some external hosts in the external network, E1 for instance. And to test the second part, the test trace will be sending some traffic from the external network, E1, to some internal network host, I1. So let's imagine what happens if we run those two different test cases in separate. So according to the policy, the test case 1 will always be allowed. And if we run in separate for the second test case, what will happen is that this test case will be dropped according to the second policy. But however, if we run them in parallel, something bad would happen. In particular, if we run them in parallel, and it is the case that the test trace in the first test case reaches the firewall first before the second test trace, then there is a chance that the traffic in the second test trace will be allowed according to the policy. So this is nothing wrong with the policy itself. Actually, you should expect that this policy is correct. What's going wrong here is that you have a wrong scheduling that gives you incorrect results. So as a result, you see some false violation of the second policy, given the results of the tool. So hopefully at this point I convinced you that naive approaches would not work if you want to schedule test cases in a stateful network. Therefore, we have to come up with a scheduling that is clever enough to schedule all the test cases in order to inject those test traces. To that end, we propose Mikado. At a very high level, Mikado is sitting between the testing tools and also the network. And Mikado will view the testing tools as black boxes. So the reason for that is that Mikado wants to allow the operators to use different tools they want in order to test different policies. And as input, Mikado takes all test traces from these testing tools. And internally, Mikado runs a scheduling algorithm and then generate a schedule that is able to parallelize the injection of the test traces. So when we design Mikado, there are two high-level goals we want to achieve. First of all, we want to make sure that the schedule will be efficient. In particularly, if we compare with sequential scheduling algorithms, we want to make sure that this is much more, we have seen much more efficient improvement compared with the naive solution. And the second goal is that we have to guarantee that our schedule always returns you the correct results. So now, with those two high-level goals, let's step back and think what an ideal solution would be if we want to achieve those goals. So the problem here is that we're given a set of test traces as shown in this picture. And a very ideal solution here is that we can partition in all test traces into different partitions. And all test traces in a partition maintains this property that all these test traces can be injected into the network in parallel. If we can maintain such a property, then a corresponding schedule will be something like we run all test cases in a partition in parallel. But if we have different traces in different partitions, then we might want to run them in sequential. So this gives us a nice framework on how to schedule test traces in parallel and also avoid incorrect results. So of course, you can imagine that a sequential scheduling corresponds to the case where each partition contains only one test case. So the goal here is that we want to minimize the number of partitions in this partitioning. So in order to achieve this framework, we can say that there are two high-level challenges. First of all, in order to make sure that running all test traces in a partition gives us correct results, we have to reason about the correctness of running tests in parallel. To achieve that, we have to develop a formal model of stateful networks and also define the notion of correctness. Second, once we have such a notion of correctness, we have to come up with an efficient algorithm to run this scheduling. So this is particularly challenging because any partitioning algorithm runs in exponential time. So perhaps we'll have to come up with smarter ideas in order to address this challenge. So now let's first talk about how we can model a stateful network and propose a notion of correctness on running test scheduling. So I'm going to use a simple example as we've seen before to illustrate the high-level idea. At the first step, we're going to assume that every device have a finite set of ports, and every port has a FIFO queue that is able to queue incoming packets waiting for processing. And since we're dealing with stateful networks, we have to model the internal states within every stateful device. In particular, we do this by modeling the states as a state map. For instance, for the stateful firewall here, the firewall may maintain a table where each entry in the table keeps a binary value for each pair of hosts in the internal and external network, respectively. Now with that, we're going to model the execution of stateful networks as a transition system, where a state captures all information of the current snapshot of the network. In particular, that snapshot will capture the information of all packets that are queued in the incoming port, and also it captures all values for every device in the stateful map. So we'll call this a state, and we're going to model one-step transition as a formula that makes one step from a state S1 to another state S2. And also, we're going to label the packets that is processed at the state S1, for instance, P1 here and P prime here. So what does this mean? So intuitively, you can imagine that we have two snapshots of the stateful network, and then by processing some packet in the stateful network at this snapshot, the network will be involved to another state. And for instance, in this case, the blue packets will be processed by the firewall and then delivered to destination. And also the internal states will be changed. So that's the meaning of this formula. So P1 here denotes the blue packets, and P1 prime denotes the packets after this processing. So we can continue doing this by adding more transitions to the network that forms a state transition system, and we call it particular a sequence of such transition or run. So this is how we can model stateful networks. So why is this important? Well, based on this modeling, we can propose a notion of correctness. At the very high level, the intuition is that we want to make sure that if we run a set of test traces, such as T1 to Tn, then we want to make sure the behavior of each test trace is going to be exactly the same as if we are running the test trace alone in the network. So formally, what can we formalize this intuition? So we're going to consider an arbitrary run from a single test trace T1. And here the initial state S1 captures only the test trace T1, denoted as blue packets here. And also we're going to consider a second scenario where the sequence of where the run of the network contains two traces, T1 and T2, denoting different colors here. So since we have two different traces, the run here contains packets from the trace T1 as well as the trace T2. If we only look at the packets appears in P1, we have to make this a guarantee that the behavior, the sequence of packets exactly match the sequence of packets as if in the first scenario. So that gives us the notion of correctness. So now we have seen how we can define the correctness by scheduling multiple tests. So what can we do in order to schedule the test traces to achieve such a correctness notion? Well, a very naive solution would be enumerating all possible partitioning to the set of states. And then for each partitioning, we check it is a case where each partition is correct with respect to the definition we proposed. And we're going to return the first feasible solution that is guaranteed to be the smallest. Well, this naive solution is optimal. However, there are key challenges that it's not going to be scalable. First of all, there are exponentially many such partitioning schema to a large set of test traces. For instance, this is a partition, and there are other possibilities. Second, even we found such a partition, reasoning a large number of test traces correct is hard. Particularly checking the correctness according to the naive definition is going to take exponential time. So we need some efficient algorithm. Perhaps we want to suffer the optimality, but we want to find efficient algorithm here. So in order to achieve the efficient scheduling algorithm, our key idea here is to check the read-write conflicts that appears in the stateful network. So to illustrate the idea, I'm going to use this example again. So remember that we have two test traces, T1 and T2. And T1 is from I1 to E1, T2 is from E1 to I1. And we also have the state map that models the state captured by the state firewall. Then what happens is that if we run T1, then T1 will access some state in the state firewall, and potentially it's going to change the value of that entry, say from 0 to 1. So now, if it is the case that T2 also accesses the same state, then the value that is read by T2 will be different. So if the test 1 did not modify the value read by the test 2 will be 0. But however, since T1 already accessed that value, then the value read by the test 2 will be T1. So that gives us the conflicts. Basically, one is writing the entry, but the other one is reading the entry, but the value will be different. Actually, we can formalize this idea, and we can prove in the paper that if n test traces is correct to run in parallel according to our definition, if every pair of them are non-conflicting. So this is particularly important because this gives us an efficient algorithm. Now we can also only look at pairwise conflict relations in order to determine whether or not there exists a correct scheduling. So our approach works as follows. First of all, we check all the conflicts among all test traces. Then we can build a graph called a conflict graph, where each node corresponds to a test trace, and one edge between two nodes denoting the conflicting relation. And given such a graph, we can color this graph using minimum number of colors, where two ends at the edge will be colored with different colors. You can imagine that if we color all nodes in the same color, then all the test traces will be scheduled in parallel together. So this gives us a natural scheduling of running multiple test traces. So we implement this framework called Mikado. At a very high level, we have these two components. First of all, we have a conflict checker, which is able to generate a conflicting graph by detecting conflicts. And then we have a test scheduling algorithm, basically running a off-the-shelf coloring algorithm that gives us a suboptimal schedule. So now let's talk about the evaluation. So first of all, we want to see whether or not we can reduce the test running time by carefully schedule all test traces we have from different test tools. In this case, we particularly considered different testing tools such as BUS, ATPG, and SIMNet. And also, we considered two naive approaches. The first approach, denoted as baseline here, is a sequential scheduling algorithm which runs all test traces in sequential. And also, we consider a little bit smarter way of scheduling those test traces, which is called MB-based. The idea here is that if two test traces will access the same middle box, we want to schedule them in different rounds. So on this figure, the x-axis is going to be the number of policies, and for each policy, we generate one trace in order to test that policy. And the y-axis is the number of rounds in order to test all these policies. As we can see that Mikado achieves reasonably good performance compared with two approaches. In particular, we see that Mikado achieves about 2 orders of magnitude speed up compared with baseline, and also there's 1 order of magnitude speed up compared with MB-based approach. Second, we want to evaluate how scalable Mikado is in terms of network size as well as the number of network policies. So this figure shows the scalability of Mikado in terms of the network size. As we can see that Mikado is reasonably good in terms of the size of the network size. We can see that the first component, which is a conflict and graph generation, takes no more than 3 minutes and scale to more than 1K nodes. And the second component is also very efficient. It can run the coloring within 1 minute. And in terms of the number of traces, we can see that Mikado runs reasonably good. The efficiency of the first component, the conflict checking, the conflict graph generation component, runs within 10 minutes, even for 10K traces. And also, the running time for the coloring algorithm is reasonably good as well. So that is not the end of story. Actually, in the paper, we propose further extensions to the basic Mikado system. We observe additional opportunities by adding this trace refiner. So the idea is that if two traces are conflicting with each other, we generate minimal information and as input to the testing tools, asking the tools to generate another traces in order to avoid such conflicts. You can see the details in the paper. To conclude, in this talk, I present Mikado, which is an efficient and correct test scheduling framework for ensembles of policies. We make 2 key contributions here. First of all, we formalize the testing in stateful networks, and we propose an efficient algorithm in terms of running the scheduling correct and efficient. And there are in the evaluation, we show we achieve a reasonably good performance. And for future work, there are 2 directions. Number 1 is how can we generate tests and also schedule them in one go. And number 2, can we check quantitative policies in order for performance properties? With that, I'm happy to take questions.
Hey, Sanjay from Purdue. This is very cool work. I have 2 questions. The first is more of a clarificatory one. How did you get your policies? So are these realistic policies, or where did you get them from?
Yeah, so the policies are obtained by doing a survey on academic and industry documents, such as documents from papers like PGA and other papers, and also some industry papers. So we collected about 40 different kinds of policies, and that gives us the policy we want to run.
I see.
Yeah.
My second one is, how do you know that these 2 policies are clearly non-conflicting? I know you talked about read-write conflicts, but can there be more complex things happening maybe in a distributed network with multiple devices and with routing changes and so on? Can more weird things happen?
Right. So first of all, at this point, we assume the stateful network, the configuration of the stateful network would not change during the testing. And number 2, so we do not check the conflicting between policies. We check the conflicts between tested traces. So that can be done by using our formal model.
Okay. Thank you.
Yeah.
Hey, so again, a clarification question.
Sure.
So when you're trying to generate these test cases, are you trying to, in general, test the quality of the service, or are you trying to test when you're introducing new policies in the network?
At this point, we do not handle quality of service policies. So the example policies, what we handle are like reachability, service chaining, access control. So those are the policies that are supported by state-of-the-art testing tools, and we're not building yet another testing tool. We are scheduling test traces.
I see.
Yeah.
And so, I mean, so with respect to scheduling, right? So typically these policies would be done, I mean, it would be introduced in a controlled fashion. Like we heard the talk yesterday from Google that when you're trying to deploy new things, new changes, you do it in the A/B fashion. So if your goal was to understand the impact of policies or policy changes, typically, I mean, early on, I mean, these are not at very high scale, right? So, and you need test cases around this, and large providers do pre and post comparison of reachability and performance metrics. So I'm trying to understand, where does scheduling come here? Because if I'm trying to assess the impact of policy changes, we have to do this for each and every policy change.
I'm not particularly understand this question. So, are you saying you want to run the policy in a live network? Is that the case?
So you're generating test cases
Sure.
for new policies, right?
Yeah, that is generated by other testing tools.
Yes,
Yeah.
but you're applying these test cases when you're changing certain policies.
Right.
Like you're changing firewall rules,
Right.
or you're making a configuration
Right.
change,
Yeah.
right?
Yeah.
So whenever a large provider does this, they have to test the impact of this change,
But where do you test them?
wherever you're making the change.
Yeah, you want to. If you test those test traces on the naive network, you have to schedule them. That's the point.
At the same time as you do the change.
Yes. Yeah, if you have multiple test traces and you want to test them at the same time, then you have to schedule them. But of course, I agree that you can do them in sequential. Test one policy and wait and test another. That will also.
Okay, good. Let's thank the speaker again, please.